Greetings. This talk presents AcouBLE, clock seeding BLE chips by acoustic signals for extended energy efficiency. In this work, we revisit the internal energy breakdown of commercial BLE chips and propose a new paradigm for significantly reducing their energy footprint while preserving full backward compatibility with BLE connectivity protocol. Bluetooth Low Energy or BLE provides a seamless ecosystem for IoT applications. In this architecture, smartphones and other smart devices such as Google Home act as central nodes, while everyday objects such as wristbands, medical devices, and trackers act as peripherals. These peripherals are typically powered by small batteries and therefore are resource constrained. Their design objective is long operational lifetime under strict energy budgets. While BLE connectivity plays a central role in enabling this ecosystem, it imposes significant energy burden, sometimes more than 80% of the total energy consumption on these devices. Prior work has largely focused on optimizing BLE protocol for energy saving, such as reducing packet length, adjusting connection intervals, or minimizing the retransmissions. We instead performed detailed power profiling on commodity BLE chips, in this case, Nordic NRF5340. Our measurements show that, contrary to our expectations, the RF components, meaning the transmitter and the receiver, account for less than 15% of the total energy consumed per BLE connection event. In contrast, the megahertz reference clock generator alone contributes to 85%, primarily due to crystal oscillator warm-up from sleep mode, which takes several milliseconds. Next, we carefully examined the internal architecture of commercial BLE chips. We found that the energy-intensive reference clock generator block can be disabled and bypassed without altering the BLE chip's functionality, provided that a stable external clock is supplied. This leads to a new paradigm. Instead of generating the megahertz reference clock internally using a crystal oscillator, we inject a stable clock from outside into the BLE device. Unlike a crystal oscillator, externally supplied clocks do not require the BLE chip to go through a millisecond scale warm-up period. Therefore, the energy overhead associated with clock generation can be eliminated. We refer to this approach as clock seeding. We believe that for any solution that is built upon BLE, in order for it to be widely adopted in practice, it needs to satisfy two key requirements, namely commodity-like deployment and backward compatibility. First, deployment must remain commodity-like. We cannot assume specialized infrastructure. The system must operate in a simple one-to-one scenario between a smartphone acting as central and the peripheral device. Second, the solution must preserve backward compatibility. We cannot modify BLE signaling or protocol behavior. Additionally, the solution cannot share a spectrum or hardware with BLE, which rules out approaches such as Wi-Fi-based clock delivery, and cannot rely on restricted technologies such as BLE. Under these constraints, the question becomes, what signal can a smartphone use to seed the peripheral's clock? We propose to use acoustic signals. Audio operates in a spectrum orthogonal to BLE, and it does not share RF hardware. And it does not involve third-party restrictions. Finally, it is universally available in nearly all smart devices. However, this introduces two major challenges. First, there is a large frequency discrepancy. Audio signals are in the kilohertz range, whereas BLE requires a megahertz reference clock. Second, the acoustic burst must arrive at the peripheral device precisely aligned with the BLE connection event. However, user space applications cannot access the BLE chip's internal transmission timing. And even if transmission timings were known, the difference in propagation speed between RF and acoustic signals makes precise alignment non-trivial. Our solution, AcouBLE, addresses these challenges without modifying the BLE protocol. No changes to BLE signaling are required, and no additional infrastructure is introduced. On the TAC side, we design a dedicated clock seeder circuit that converts a kilohertz acoustic burst into a stable 32 megahertz reference clock. On the smartphone side, we design a lightweight feedback-based timing mechanism that operates entirely in user space. To realize AcouBLE in practice, several design challenges must be addressed. On the tag side, the first challenge is achieving an extremely large frequency of conversion factor, converting an approximately 18 kHz acoustic input into a stable 32 MHz reference clock, corresponding to more than 3 orders of magnitude increase. The second challenge is preserving ultra-low phase noise throughout this aggressive conversion process in order to meet the strict reference clock stability requirement imposed by commodity BLE chips. The third challenge is ensuring robustness to wide variations in received signal amplitude, which can fluctuate significantly depending on the distance and orientation between the smartphone and the peripheral device. On the smartphone, the BLE ping and the acoustic burst must arrive at the peripheral at the same time to ensure proper operation. However, smartphone applications do not have access to the BLE chip's internal transmission timestamps. Additionally, RF signals propagate at the speed of light, while acoustic signals propagate at the speed of sound. Given that the distance between the devices is not known, simply transmitting both signals simultaneously does not guarantee alignment at the receiver. Therefore, direct scheduling is insufficient. Let us first discuss the tag design. The acoustic burst is first captured using a MEMS microphone and amplified using an audio amplifier. The signal then passes through a duty cycle evener to stabilize its waveform. Next, we perform a staged frequency of conversion. At frequencies below 1 MHz, digital circuits work more efficiently than analog filters and harmonic conversion circuits. So we use our novel triangular frequency doubler stages to progressively increase the frequency from approximately 18.5 kHz to around 1 MHz. After reaching the megahertz range, digital circuits become power hungry, while analog circuits can be designed more efficiently. So we employ analog harmonic conversion stages to reach from around 1 MHz to the final 32 MHz reference clock. To address the burst alignment with BLE connection events, we developed the lightweight feedback-based protocol. During the initial connection event, the smartphone transmits a BLE ping along with an acoustic burst. Upon reception, the tag measures the difference between the BLE ping and the acoustic burst. We denote this difference as delta T. The tag embeds delta T in the payload of its BLE response. The smartphone receives this response and adjusts the timing of the subsequent acoustic burst accordingly. After only 3 connection events, the system converges to near perfect alignment. This mechanism operates entirely at user level, requires no system level API access or routing privileges. Also, it does not require distance estimation or any modification to a standard BLE protocol. We implemented a prototype of the clock seeder using off-the-shelf components and evaluated its signal integrity and end-to-end performance in various setups and environments. Our measurements show that the clock seeder hardware prototype implemented with off-the-shelf components reliably converts an approximately 18.5 kHz acoustic input into a 32 MHz clock with sufficiently low energy, low jitter to satisfy commercial BLE chips requirements. Finally, we compared packet delivery rate and energy consumption against the commercial BLE tag operating with its internal crystal-based clock generator. AcouBLE achieves nearly identical packet delivery rate. At the same time, it reduces the energy footprint per connection event by a factor of 3.3 to 5.9 times. This improvement stems directly from eliminating the reference clock warm-up overhead via clock seeding. Thank you.